On Monday, we just start to give the definition of standard basis vectors. So in R square, if you are in two-dimensional space, those are the vectors, two vectors of course, I and J. Mikrofonumuz açık kaldı birimize. So in R square, in two-dimensional space, the standard basis vectors are I and J. I is from origin to point 1, 0, the vector, and J is the vector from origin to the point 0, 1. So that means you can express the vector I with vector parentheses, let's say, with vector parentheses, with those vectors, one by components 1 and 0, and J by 0 and 1, that means. So, like we said, we will call them standard basis vectors in the two-dimensional space for here. And any vector in two-dimensional space which start from the origin, so the initial point is origin and the terminal point is xy, has components xy as we expressed on Monday, and we write it by those parentheses, and by in terms of our linear combination of those standard basis vectors, we will write them, the vector r, as x times I plus y times j. Okay, so any vector in two-dimensional space which is from the origin to the point xy can be expressed by standard basis vectors as x times I plus y times j. And in the first form, here, this one, we specify the vector by listing its components between angle brackets, which express the vector components. And in the second, here, like we said, we write R as a linear combination of standard basis vectors I and J. There should be arrow here because those are vectors. I forgot to write. And the vector R here is called position vector because it will start from the origin and to the xy, so it will start from the origin. And we will call that vector R is position vector of the point xy. And position vector, like, okay, is tail at the origin and its head at the point, okay, the initial and the terminal points respectively, whose position is specifying, and the length, of course, will be the square root of x squared plus y squared. So this will be the length of the vector R in two-dimensional space. If we are not talking about position vector of any vector AP, which has not the terminal point as origin, so the A is AB here and B is BQ, can be also expressed as a linear combination of those standard basis vectors I and J. So first, let's express the vector AP, or the vector from A to P. So it will have components P minus A and Q minus P. So those will be the components of the vector AP. And if you try to write it in the form of linear combination of the standard basis vectors, it will be p minus a times I plus q minus b times j. So this is any vector in two-dimensional space with initial point not the origin, so any point. You can express that vector as a linear combination of I and j, which are standard basis vectors in two-dimensional space. So this is the expression. And let's also talk about the zero vector. We said that on Monday we need to have the zero vector in even in n-dimensional space, because if you have the scalar multiplication in two-dimensional space, let's say here, so that means we can multiply 0 by I and also 0 by j, and you have the sum in two-dimensional space, so it is defined also, and it is closed in two-dimensional space. That means if you add those two to each other, it should express a vector in two-dimensional space. So that means if you multiply 0 by I and if you add it, the multiplication of 0 times j, so which will be 0, as you can guess. So there should be a vector which we will denote by this notation, and we call it zero vector in two-dimensional space. And we said also it has length 0, and of course there is no specific direction for zero vector. For any vector u in two-dimensional space, we have always that also there should be an arrow above that u, since it is a vector. So u times 0 times the vector u is equal to 0 vector. Here 0 is, that 0 is scalar of the scalar multiplication in two-dimensional space. And we will call unit vector a unit vector, which is a vector of length with length 1. So we can say that basis vectors we have I and j are unit vectors. Also there will be another notation for the vectors who has length 1, or who are unit vectors. Instead of this arrow that we use to express vector, we can use the head. We will in later page we will see that. So instead of this, if this is any vector with length 1, you can use the head above that vector, but it is okay if you just define them by that arrow. And if you have any non-zero vector v, okay, it is here, we can form a unit vector, and we will express it by that head above in the same direction of v by multiplying v by the reciprocal of its length, so which will be a scalar, of course. So this is your vector v, which is not a unit vector, any non-zero also vector. Then if you try to express a unit vector in the direction of v, so you want v in the same direction, but you want it with a length 1, of course, so you have to multiply it by 1 over the length of v. So that will now express v over the length of V will express a unit vector in the same direction of vector V. This is another way that you can show the vector, the unit vector, or the vector with length 1. Let's give some examples for addition and also scalar multiplication, subtraction. Here we have. So the point A is 2 minus 1. By those parentheses, we express points in n-dimensional space. So here it is a point in 2-dimensional space, as you can see, since it has 2 components. But if you have those so if you have those angle brackets like here, so those will express the vector in n-dimensional space. So they didn't express their points, but we know that from the expression. A is 2 minus 1, B is minus 1, 3, and C is 0, 1. And after that, first we should express actually AC, CB to compute 2 times AC minus 3 times CB, the vector CB. So let's first try to find the vector AC. Then it is from A to C. That means it will have components 0, minus 2, and the other component will be 1, minus, minus 1. So if you write it as a linear combination of standard basis vectors, it will be minus 2i plus 2j. So this is the vector AC. And let's also find CB. So the vector will start from C and it will end with B. Then the first component of vector should be minus 1, minus 0, and the y component should be 3, minus 1. So if you write it as a linear combination of standard basis vectors in 2-dimensional space, it will be minus 1i plus 2j. Of course, you can express those vectors by angle brackets by minus 1, 2. Okay, so you can write it in that way. So let's compute 2 times AC, and also we will compute minus 3 times CB. So this is a scalar multiplication of vectors. 2 is any scalar, so you need to multiply the components of AC by 2, or you make them double, you can say. It will be a same direction. It will have a same direction. 2 times AC will have same direction with AC, but the length will be double of AC. So this will be a vector with components minus 4i plus 4j as a linear combination of standard basis vectors. And if you compute minus 3 CB, then that will be with the opposite direction of CB and 3 times more has 3 times more, the length will be 3 times more than CB. So it will be plus 3i minus 6j. So if you, after that, if you compute the I, it will be minus 4 plus 3, I will be minus I, and if you compute the j component and y component of 2ac minus 3cb, it will be 4 minus 6, which will be minus 2. Of course, you can write it in the by the parentheses, the angle brackets, as minus 1, minus 2. So, what are the properties of vector operations? Here, those vectors can be in any dimension which are greater or equal to 2. So, u, v, and w are vectors, let's say, in general. U plus v is equal to v plus u. So, the addition is commute in n-dimensional space. That means u plus v parenthesis plus w is equal to u plus the parenthesis of v plus w, and u minus v is equal v plus minus 1 times v. See, it is a scalar. You can write the subtraction as scalar multiplication by minus 1 with minus 1. And the last property, if t is in a scalar here, t times the parenthesis of u plus v is equal to t times u plus t times v. So those are algebraic properties in, you can say, n-dimensional space even, where n is greater or equal to 2. And like we said, we will generally deal with vectors in 3-dimensional space. So let's try to see how will be the representation of standard basis vectors that we see for 2-dimensional space. So given a Cartesian coordinate system in 3-dimensional space, here we define 3 standard basis vectors, as you can just guess, and we will denote them by I, J, and K, and actually they represented by arrows from the origin to the points 1, 0, 0, 0, 1, 0, and 0, 0, 1 respectively. Any vector in 3-dimensional space, that means, can be written as a linear combination of those standard basis vectors. For example, if you try to write the position vector of the point x, y, z, that means you try to write the vector which has initial point origin and the terminal point as x, y, z, then you can write that by that angle brackets x, y, z, and also you can write it as a linear combination of the standard basis vectors in 3-dimensional space. So it will be x times I plus y times j plus z times k. So you can actually find it by using you can find it. It is equal to the same vector by using the algebraic properties that we have seen above. So it will give x times the vector 1, 0, 0 plus y times the vector 0, 1, 0 plus z times the vector 0, 0, 1. Then after you use the scalar multiplication and also addition in 3-dimensional space, the properties, then you can get, it will be a vector with components x, y, and z. Let's see example in 3-dimensional space here. So as a vector, we have u and v. So they write it they should write it here in, they are both in three-dimensional space, because as you can see for v, vector v, you don't have the k component. So if they don't express that, you can think maybe it is a vector in two-dimensional space. So that is why they should write it here. They are two vectors in three-dimensional space. So let's I will briefly express the vectors, not as the combination of linear basis vectors, standard basis vectors, but just by the components. So u is the vector -1, 3, 1, and v is the vector 4, 7, and 0. Since we don't have k component, we don't have the linear, the standard basis vectors k here. Pardon. And we try to find 2 times u plus 3 times v, also u minus v, and at the end we try to find u of the length of 1/2 times u. First we need to compute 2 times u, so if you just multiply u as with 2, so it will be a vector with components -2, 6, and 2. And if you compute 3 times v, it will be a vector with components 12 and 21 and 0. And after that, you should just do the addition between vectors. So it will be -2 plus 12, which will be 10i. So this will be the first component of the vector 2u plus 3v, and 6j plus 21j will be 27j, plus 2k plus 0k actually will be 2k. So the components of 2u plus 3v, the vector, will be 10, 27, and 2. And let's find u minus v, which means you will add -1 times v to the vector u. So u will be just the same. So you need to multiply vector v by -1, so it will be -4i minus 7j. And you will do the same addition rule here for the u minus v. So it will be -1 minus 4i, so which will be -5i, 3 minus 7j, so which will be -4j, and plus k minus, let's say, 0k, so which will be k. So the components of u minus v are -5, -4, and 1. The last one will be, of course, not be a scalar vector. It will be a scalar, because we need to find the length of 1/2 times u. Actually, we try to find the length of the half of the length of u, let's say. So first we will do the scalar multiplication here to find 1/2 times the vector u. It will be -1/2 plus 3/2 plus 1/2. Okay, sorry, -1/2i plus 3/2j plus 1/2k, and the length is actually -1/2 square plus the square root of minus 1 over 2 square plus 3 over 2 square plus 1 over 2 square. So if you compute that square root, it will give 1 over 2 square root of 11. So this will be the length of u over the vector, or 1 over 2 times u, or the vector u over 2. Now here, after these algebraic operations in three-dimensional space, we will talk about a product which we'll call as dot product, or we will call it as scalar product, we will see. And also we will talk about the projections. So let's first start by the definition of dot product. If you have two vectors in two-dimensional space in R2 as with components, U has components u1 and u2, and V has components v1 and v2. So actually the dot product will be denoted by that big dot here, and it will denote a scalar. So that's why we will also call it scalar product, and it is the sum of the products of their corresponding components. So actually the dot product, or the scalar or inner also product, it can you can say. So u dot product v is equal to u1 times v1 plus u2 times v2. So it is the sum of the product of those vectors corresponding components. And you can also use scalar and inner product instead of dot, so they will express the same thing. And similarly, of course, we can define the dot product in three-dimensional space. So if we let u as a vector in three-dimensional space with components u1, u2, and v3, and v is a vector with components v1, v2, and v3, then the dot product of u and v is equal to u1 plus v1 plus u2 plus u1 times v1 plus u2 times v2 plus u3 times v3. So you can generalize it in three-dimensional space. And what are the algebraic properties of dot product or scalar product? Let's remind it again. Since you have the scalars as a components of any n-dimensional space, so that means from u times v1 you have a scalar, because u1 is scalar, v1 is scalar as a first component of u and v respectively. So this will be a scalar, and that one u2 times v2 will be a scalar, u3 times v3 will be a scalar. That means if you add those three scalars, then you will of course find a scalar. That is why you can also call that product as scalar product. So let's try to see, after that expression, after the definition of that product, what will be the algebraic properties. So of course you can write this expression of scalar product as v1 times u1 plus v2 times u2 plus v3 times u3, because in real numbers you have that rule. That means u dot product v will be equal to v dot product u. or scalar, you can say. So this is that means the dot product is commutative. U times the parenthesis of v plus v, this is vector addition, is equal to u times v plus u times w. So that means you have here actually the multiplication property that we have for real numbers, right? And also you can check it by using the definition of addition in vectors, also by the definition of dot product. As t, any scalar here, since there is no arrow above it, it is a scalar here. T times u dot product v is equal to u dot product t times v, and also it is equal to t times u dot product v. Also, this is easy to see again by using the dot product definition expression and also the scalar product of vectors. At the end here we have the dot product u and u. So if we let u as the same vector here with components u1, u2 and u3, then that means the dot product is u1 square plus u2 square plus u3 square. So which is actually the square of the length of u, since the length of u is square root of u1 square plus u2 square plus u3 square. So if you just take the square of that square root, it will be the dot product of u and u. So those are important algebraic properties that we will use for dot product. So maybe you wonder why we have such a product that we call dot or scalar product. After trying to find the angle between any two vectors in n-dimensional space, there will be always a solution which includes that expression. For example, for the two-dimensional space, they find such a sum. Okay, so that is why they need to express such a multiplication that you can define in any n-dimensional space which is greater or equal to 2. So after that, we of course need to define the angle. What is the relation between the angle between two vectors and the dot product? So if theta is the angle between the directions of u and v, or the vectors of u and v, and theta is in between 0 and pi, then u dot product v is equal to the length of u times the length of v times cosine theta. In particular, you can directly say u dot product u is, it should be, okay, v it is given in a general way here. So u dot product, if u dot product v is 0, that means u and v are perpendicular to each other, because theta need to be 90 degrees. Also, you can say if two vectors are perpendicular to each other, then that gives from cosine 90 degrees u dot product v has to be 0. So that is why we have here if and only if theorem in the case. And also the vector, the 0 vector, is perpendicular to any vector. That's why if you talk about the dot product of any vector and the 0 vector, it has to be 0. Also, you can say here for the right side of the theorem, you can say the 0 vector is perpendicular to any vector. Let's try to see the application for dot product. If U is a vector with components 1, -2, and V is a vector with components 6, 3, and 2. Let's try to see the dot product. So it has to be 1 times 6 plus -2 times 3, and what is that component was -2 for x, so -2 times 2. After you compute those, it will be 6 plus -6 plus -4, so which will be -4. So U dot product V is -4. And now we will try to see also the angle between U and V. So to do that, we need to compute the length of U and V. First, we will compute the length of U, which will be square root of 1 square plus -2 square plus -2 square, which will be 3. And then the length of V will be square root of 6 square plus 3 square plus 2 square, which will be 7. And by the definition of dot product that we see, okay, what we see here. So you can say arc cosine theta of U dot product V over the length of U times the length of V will be equal to theta. So we will try to see what is approximately the theta is. It is, if we just let the scalars that you find by those 3 values, and you will see theta is approximately 1.76 radians. So always keep in mind that if you have that, or you can say scalar product, you need to find always a scalar. So if you find a vector, that means you do something wrong. So keep it in your mind that, because we will see on 10.6, we will see here the cross product, which will be a vector, not a scalar. And for the last, last definition here, we will talk about scalar and vector projections. So projections, and generally we will talk about projections in 3-dimensional space. The scalar projection S, that is denoted by S, of any vector U in the direction of non-zero vector V is the dot product of U with a unit vector in the direction of V. So it has to be a number, because we are talking about a scalar projection. So it has to be, that means you try to find a vector in the direction of non-zero vector V, and also it has to be with the dot product of U, but it should be a unit vector in the same direction of V. So that means you have as U dot product V over the length of V. so which can be also written by using the definition of the dot product here. So you can write, instead of u dot product v, you can write the length of u times the length of v times cosine theta. So the length of v will be common factors, and if you cancel those, then you will get the S, the scalar projection of any vector in the direction of non-zero vector v, will be the length of u times cosine theta. Of course, theta is an angle between those two vectors. And we will denote the vector projection with that notation. Of course, it will define a vector. So this will be the notation of the vector projection of u in the direction of v. So here as a sub, we will write the direction, okay, and it will be the scalar multiple of unit vector v in the direction of v by scalar projection of u in the direction of v. So that means the vector projection of u in the direction of v, which is denoted by this term, and it will be equal to u dot product v over the length of v times the unit vector, which is in the direction of v. And if you just write this, the unit vector in the direction of v, as the vector v over length of v, then that means the vector projection of u in the direction of v can be written as u dot product v over square of the length of v times v, the vector v. And here the scalar projection that we defined by S is the length of, so it will be the length of S is the length of line segment along the line of v, vector v, obtained by dropping perpendiculars to the line from the tail and the head of u. Also, S will be a negative value if theta is greater than 90 degrees because of cosine values, for those values of theta, cosine theta. And it is often necessary to express a vector as a sum of two other vectors parallel and perpendicular to a given direction. Let's try to see what it means here. We will try to express the vector 3i plus g as a sum of vectors u plus v, where u is parallel to the vectors I plus g and v is perpendicular to u. So you try to write it by those rules here. So u has to be parallel to this one, and v has to be perpendicular to u. We try to write 3i plus j as a sum of u plus v. So here we have two methods that we will use to write it in that way, to write 3i plus j in that way. First, we will use vector projection here. So in that way, u must be the vector projection of, since it is parallel to I plus j, and also it should be the vector, one of the vectors that you try to write it as a sum of 3i plus j. So it should be the vector projection of 3i plus j in the direction of I plus j. since it is parallel, it should be in the direction of I plus j. They should have the same direction. Then that means by vector projection, u can be defined as the vector projection of u on 3i plus j. So you will multiply 3i plus, you will try to compute it as 3i plus j dot product I plus j over I plus, the length of I plus j square times I plus j. So this is directly comes from the vector projection of 3i plus j in the direction of I plus j, and by using this you will directly find it is equal to 2i plus 2j. So this is the vector u. After that there will be just one step, because you try to write 3i plus j as a sum of u plus v. That means 3 plus j minus the vector u will give the vector v. Then you will subtract u from 3i plus j here. So if you do that computation, it will give 3 minus 2i, which is 1i, plus 1 minus 2j, so which will give minus 1j. So this has to be the vector v then. So this is just for using the vector projection. So if we use as a second method here, basic principles that we have for scalar multiplication as a parallel, if you have parallel vectors and if you have perpendicular vectors. If you have parallel vectors, that means from the definition of dot product here, that means you have cosine 0, no? There should be, but we will use here the perpendicular, okay? The perpendicular, and also it has to be a constant scalar multiple of if two vectors are parallel, that means one is the scalar multiple of the other one. We will use that. And for the perpendicular case, we try to use the scalar multiplication, because we have cosine 90 is as 0, so that is why we will use that. So let's again see the question. U should be parallel to u plus g, so that means u can be written as t times u plus g. So t is any scalar here, so which makes u and I plus j as two parallel vectors, and also v is perpendicular to the vector u. That means u dot product v is equal to 0, because cosine 90 degrees is 0, so it has to be 0. But here, as you can see, they didn't let t, since this should be u, but they didn't let t, because it doesn't matter if you even multiply by t or without t, this u, it has to be, those two vectors has to be perpendicular. So if you just multiply v by I plus j by scalar multiplication, it has to be 0, of course, since those are parallel. So you need to write, you should conclude it, those vectors, the scalar multiplication of those vectors has to be 0, since they are perpendicular to each other. And also, this is the question. This was the question. You try to write 3i plus j as a sum of u and v. So let's take the dot product of this equation, I plus j. So we will write here first the dot product of this equation we have. So if you multiply this equation with the dot product with I plus j, so you have dot product from both sides of this equation with I plus j. It will be, by using the properties of dot product, algebraic properties of dot product, we see it has to be u dot product I plus j plus v dot product I plus j equals 3i plus j dot product, also you can do it in that way, dot product I plus j. So let's write, instead of u here, let's write t times I plus j, t times I plus t times j, or so it will be here, the first part here will be t times I plus j dot product I plus j, and for here, since those two vectors are perpendicular, we know that scalar multiplication is 0. So if you do just the first scalar multiplication here, we know that it has to be, it comes from here. It has to be 3 times 1 plus 1 times 1, so which has to be 4. That means 2t t plus 1, sorry, t times okay, t times 1 here you have, plus again t times 1 from the dot product, so it will give you 2t. So from the scalar product here you have 2t plus 0 is equal to 4, which gives the scalar t that you try to represent the vector u, which is parallel to I plus j, has to be 2. That means that scalar has to be 2. It yields that u has to be vector with components 2 and 2 from the definition that you have here, and v has to be the subtraction of u by 3i plus j. So also it will give you directly 3 minus 2i plus let's say 1 minus 2j, which will be the vector v with components 1 minus 1. So this will be the second method, which is much longer than the first method to see 3i plus j as a sum of u plus v with those rules for u and v, vector v. So if you use vector projection, it is much easier to find u and v, of course. Burada da başka bir şey yok herhalde bahsedeceğimiz. Herhangi bir sorun var mı burada? Any problem until here? 10.3'e başlayamayacağım herhalde çünkü zaten zamanımız doldu. Orada bahsedeceğimiz vektörel 3 boyutlu uzaylarda vektörel bir çarpımdan bahsedeceğiz. Cross product ya da vektör product olarak adlandıracağımız. Bir skaler olmayacak biraz önceki dot product gibi, tabii ki de adı üstünde bir vektör oluşturacak bu çarpımın sonucu. Ve sadece yine aynı şekilde 3 boyutlu uzayda olması da bu. Sadece iki vektör arasında 3 boyutlu uzayda tanımlı olması da önemli bir şey. Cross product Türkçe konuşacak olursak. Burayı başlamayalım. Cross product'ta. Burada kafanıza takılan bir şey var mı? Onu sorayım. Kalsın açık slide. Zaten yine online olacağız ofis saati için. Dersi sonlandırayım. Sorusu olan varsa kaydı durduracağım.